All right. So let's erase this. And I think we only have time for one more. So I'm going to just pick and choose. And for those of you, for me accidentally skipping, chlorine tetrachloride is a tetrahedral shape because, and if I was to quickly draw this out, uh, carbon is bonded with chlorines with no lone pairs, so it's just a 1, 2, 3, 4. It's a 4 to 0 coordinate plane. It's a tetrahedral, and its bond angle is 109.5 degrees. All right. Maybe you don't need the 0.5. Maybe 109 will be enough. I'm not sure how it was taught, so I guess the more the specific, the better. So I guess we'll do one last one. And we'll do this example, mainly because it was on your midterm review packet, and if you were stumped on it, we can do it just to clarify any doubts. So let's do that. So let's copy it down. All right. So first thing we have to do is calculate the number of valence electrons. All right, calculate the number of valence electrons. So sulfur, if we were to draw its electron configuration, is 1s2, 2s2, 2p, let's double check. 2p, oh, I'm sorry. It's way past that. So 2p6, it's 3s2, 3p, 3p1, 2, 3, 4, so 3p4. All right, and to just double check my work, okay, we're good. So we know that our third energy level is our outermost energy level, in which there are 2 electrons in the s and 4 electrons in the p, so we know that total sulfur has 6 valence electrons. We'll add that to 6 times whatever fluorine's valence electrons are. Fluorine has 7 valence electrons. Mainly because it's a noble gas. It's a halogen, so it can only have 7 valence electrons. I'm not going to draw out our electron configuration for fluorine. You can do that if you need a reference point, but you have to take my word for it. Fluorine does have 7 valence electrons. All right, and we'll pick out our least electronegative element, which is sulfur, because we know our most electronegative is fluorine on the periodic table. Our most electronegative element is fluorine, so sulfur will be our central atom. And we'll draw out all of its valence electrons for sulfur, but let me first make the calculation. 6 plus 42 will be 48 valence electrons we have to show. And maybe we may run out of space. So I'm going to draw this kind of small. So sulfur will be our central atom, in which we'll draw out our electrons. So 1, 2, 3, 4, 5, 6. So now we have 6 fluorines, and we have to figure out exactly what we can do. Well, wait. And remember, for the last one, I said we have to look for the electrons that really, really need another electron. So our topmost priorities are this electron and this electron, because they're not paired with any other electron. So we know that we should add a fluorine here. And let me do it in a different color, just so we can differentiate between our central atom and our terminal atoms. So F, F. All right. We know that these 2 places really, really need that electron to be shared with. But we still have, we used 2. We still have 4 more fluorines that need bonding. But wait, 4 more fluorines, we have 1, 2, 3, 4 electrons that are left. So we can bond each fluorine with each electron. And many people might automatically put up a red sign and say, whoa, whoa, whoa. Now sulfur exceeds its octet. It has more than an octet, because if you have a bond here, 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 1, 2, 3, 4, 5, 6, 6 times 2, you have 12 electrons for sulfur. How is that possible? You have to have an octet for sulfur. You have to keep in mind that sulfur is an exception to octets. The only ones that need to, subdue themselves to the octet rule are the ones in the second energy level. Specifically, carbon, nitrogen, oxygen, and fluorine are the main ones that need to have an octet. If you're in the third energy level, like sulfur, you can in fact exceed your octet. Because in your third energy level, you have a S subshell, a 3D subshell. In the third energy level, you have a D subshell, and also you have a 3p subshell. So you can fit more electrons. So sulfur, in fact, will exceed its octet rule. So let's finish drawing our valence electrons for fluorine. And keep in mind, I didn't want to put another electron here because then you can't really share electrons. So I want to keep this with one electron and keep this with one electron. And because we're kind of running out of time, I'm going to draw lines here to represent 2 electrons, just so I don't have to draw each one individually. But the lines mean 2 electrons. And let me redraw this. 2, 3, and then keep an electron like that so I can bond very easily. 1, 2, 3, and then keep an electron. 1, 2, 3. And once again, these lines just mean 2 electrons. This line is nothing but 2 electrons, okay? And now let's do bonding, okay? So this electron will share with this electron will share with that, this with that, this with that, this with that, and this with that. And now we have 1, 2, 3, 4, 5, 6. We used all our fluorines, and we used all the electrons that sulfur has to provide to help fluorine reach its octet. Because fluorine technically has 2 electrons now because it's sharing sulfur's electron. So fluorine has an octet here, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. All the fluorines have an octet, and sulfur, because it can exceed its octet, we don't really mind how many electrons it has. But if you want to know, sulfur has 2, 4, 6, 8, 10, 12 electrons for sulfur, and all the fluorines have an octet. Let's do our last step, which is double checking our work. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. We know that we have 48 electrons in our Lewis structure. 48 electrons is what we calculated. We know we got it right. And lastly, for our geometric or our VSEPR shape, there are no lone pairs, but there are 6 outer or terminal atoms is what we like to call them. So it's a 6-0 relationship. So it is in fact a octahedral, and I don't know if I spelled that correctly. Octahedral, or is it octo? Octahedral, and it is simply just 90 degrees for its bond angle. All right, so octahedral 90 degrees would be its VSEPR shape. There will be another video on how to memorize your VSEPR structures, what this coordinate system even means. And it's a handy way to memorize it, but I'll explain what the coordinate system even means, and hopefully that can help you understand how to quickly identify these geometric shapes. Hopefully this video helped you out in identifying Lewis structures. If you do have any more additional questions, please do come to the Applied Science meeting on Wednesday. Let me make sure what the date is. On Wednesday, December 14th, we will be having a honors, AP, and general chemistry midterm review. So this concept will definitely be covered in that meeting. Thank you very much, and I hope you tune in for the next video.